A fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth on December 17th. Comet, asteroid, or something else? A Harvard astrophysicist believes there's a strong likelihood this is a craft of alien origin, and the implications, obviously, for humanity would be profound.
A new visitor has swept through our solar system. One that is rewriting the rules of cosmic behavior and sending ripples through astrophysics. The object known as 3I Atlas is an interstellar comet, hurtling through at breathtaking speed and manifesting strange behaviors. Among them, what appears to be a bending of the solar wind around it. While comets have long been familiar to us, this one carries a sense of the alien, of something born beyond our sun's domain, and behaving in ways that challenge what scientists had come to expect. It is the bending of the solar wind, that constant stream of charged particles emanating from our sun that now demands attention. At the moment, the scientific community is puzzling over what exact mechanism is at work, why this object is interacting with the heliosphere in unexpected ways, and what the broader implications might be. Before we start, smash the like and subscribe buttons for more updates. 3I Atlas was first detected in early July 2025 by the asteroid terrestrial impact last alert system Atlas in Chile, moving faster than any previously observed interstellar visitor. Its trajectory is unmistakably hyperbolic, an indication that the sun is not the original home of this object and that it will not bind to our planetary system. But what began as the story of a rare interstellar wanderer has taken a curious turn. Astronomers now report that 3I Atlas might be influencing the solar wind in ways never before recorded. It is not merely traveling through and being buffeted by the solar wind. It appears to be bending and redirecting the flow, creating a complex interaction zone. The degree of this interaction gives rise to profound questions. What properties must an object have to exert such influence? How does the dynamic environment of the heliosphere respond? And what does this mean for our understanding of both comets and interstellar matter? To appreciate the significance of what appears to be happening, one must first consider what the solar wind is and how typical comets behave. The solar wind is a continuous outflow of charged particles, mostly electrons and protons, from the sun's corona, streaming outward through the solar system and carrying with it the sun's magnetic field. It shapes planetary magnetospheres, contributes to auroras, and defines the heliosphere, the bubble of solar influence that envelops the planets. Under normal circumstances, when a comet enters the inner solar system, its nucleus warms and volatile ices sublimate, generating a coma of gas and dust and typically two tails. A dust tail pushed away from the sun by radiation pressure, and an ion tail, shaped and carried away by the solar wind's charged particles and embedded magnetic field. The comet is largely passive in this environment, responding to external forces rather than imposing them. This is why what we're seeing with 3I Atlas is so remarkable. Instead of simply being shaped by the solar wind, it appears to be influencing the wind's behavior in its vicinity. Observations have revealed dust emission on the sun-facing side of the object and tail features not strictly aligned with the classic anti-solar direction. In particular, there is evidence of a plume or emission directed toward the sun, and reports that dust is being ejected sunward, opposite to the usual comet tail orientation. That in itself is weird. What makes it even richer is the suggestion of bending or deflection of the solar wind around this entity, hinting at some combination of magnetic interaction, outgassed material, and a previously unobserved mode of comet-solar wind interaction. Imagine a boat traveling through water. Normally the water flows past the boat, and the boat leaves a wake behind. But if the boat has thrusters that push the water aside or generate vortices, then the flow around it changes, perhaps curling, diverting, or creating eddies. What is being suggested for 3I Atlas is something analogous in the solar wind. Not only is the comet moving through the wind, but its own properties may be altering the local wind flow, causing deviations from the expected streamlines of plasma and magnetic field lines. What could be producing such an effect? Several candidate hypotheses are currently under discussion. One possibility is that 3I Atlas carries a strong magnetic field or has acquired an induced magnetic environment due to its motion through the wind. If the object is coated in conductors or has a charged dust layer, it might set up a magnetic perturbation, which in turn could influence the nearby plasma flow. Another possibility is that the outgassing from the object is much stronger and more directed than usual, injecting charged particles or neutral atoms that become ionized and join the solar wind flow, creating a local obstacle or shock. The interplay of dust, gas, charge, and magnetic fields may combine to create a bow shock or magnetosphere-like structure around the comet, altering the wind's trajectory. Also intriguing is the object's age and origin. 3I Atlas appears to have been traveling through the galaxy for billions of years. Its hyperbolic path suggests it originated in another stellar system, was ejected long ago, and entered our solar system at very high velocity. Estimates suggest it could be between 3 and 14 billion years old, potentially making it older than our Sun. Over such timescales, it would have been exposed to cosmic rays, interstellar dust, and radiation in ways that solar system comets are not. Its composition may therefore reflect those vastly different conditions. The detection of unusual chemistry, elevated levels of nickel and cyanide for example, further underscores its anomaly. That unusual chemical makeup could play into how it interacts with the solar wind. Outgassing of exotic materials might generate stronger or differently directed charges, the nucleus might have an unusual porosity or electrical conductivity, or the dust cloud might become partially ionized in unexpected ways and act as a plasma lens. Because of these combined peculiarities, interstellar origin, unique composition, sun-facing plume, anti-solar tail behavior, and now solar wind bending, the phenomenon raises important implications for astrophysics and heliophysics alike. For one, if this object can bend the solar wind, then it challenges the notion that comets are always passive participants in heliospheric interactions. It implies that under the right conditions, a relatively small body moving through the wind can create a significant perturbation that opens questions about how many other objects might be doing this unnoticed, and whether our models of comet-solar wind interaction need revision. From a heliophysics perspective, this is a laboratory unlike any we have before. We have the solar wind as a fast-moving plasma, structured by the sun's magnetic field and by turbulence interacting with a foreign body with potentially unique physical properties. Observing how the wind bends, slows, diverts, or even spirals around the object could reveal new insights into plasma flow around obstacles, magnetic reconnection, charging of dust and plasma boundaries in space, and the behavior of non-standard plasma obstacles. These insights might feed back into better understanding of how, around planets and moons and other bodies, the solar wind can be shaped by the local object's properties. We may be able to refine our knowledge of the bow shock in front of Earth's magnetosphere, or how solar wind interacts with Mars's weak field, by examining this extreme case. From the astrophysical side, 3I Atlas offers a peek into material that came from beyond the solar system. If its interaction with the solar wind is stronger than typical, that might imply that bodies ejected from other stellar systems have different surface properties, perhaps more metallic, more charged, more porous, or structured differently. That in turn suggests that planetary formation and small body evolution in other systems might yield objects that behave differently from comets we've grown familiar with. If interstellar comets can perturb the solar wind in this way, then we gain a new window into the electrical, magnetic, and plasma aspects of interstellar bodies beyond simply chemical composition or trajectory. Furthermore, the fact that 3I Atlas shows a sun-facing dust plume rather than purely an anti-solar tail adds to the intrigue of how the solar wind and radiation pressure interplay with the body's emissions. The sunward emission of dust implies that the surface facing the sun is strongly active, perhaps because the object has a pole pointing toward the sun, or because its structure is such that sublimation is concentrated on the sunward side. That focused emission can act as a directed outflow of material, which in combination with the solar wind flow creates a kind of local engine, driving a reverse tail or plume. In effect, a complex interaction ensues, dust and gas released on the sun-facing side, solar wind impacting the cloud, magnetic field lines threading through and around the ejected material, all of which may conspire to redirect flow. The end result? A bending or redirection of solar wind that is not predicted by simple comet models. The potential for plasma instabilities and magnetic reconnection in the vicinity of 3Y Atlas is also compelling. The solar wind is magnetized, carrying the interplanetary magnetic field. When it encounters an object that is emitting neutral gas and dust which becomes ionized, one can imagine local current sheets, magnetic draping, and piled-up field lines. If 3I Atlas is moving rapidly through the plasma, it may generate a bow wave of compressed plasma and magnetic field ahead of it. Or, if it has a magnetized region, it could deflect the wind around a mini-magnetosphere. The bending of solar wind could therefore be the signature of magnetic line draping around the object, akin to what happens around non-magnetized planets like Venus or comets with strong ion tails, but taken to an extreme due to the unusual combination of velocity, composition, and activity exhibited by 3I Atlas. Another dimension is the velocity of this object. Because 3I Atlas is moving at extraordinary speed, far faster than typical comets bound to the sun, it experiences the solar wind in a high dynamic regime. The relative velocity between the comet and the solar wind is greater, so any interaction is more energetic, shorter in duration, and may involve more abrupt plasma processes. That means that the threshold for generating disturbances is lower. The response of the solar wind might be more dramatic. The bending of the wind could therefore be partly a function of the object's high encounter speed. Rather than slowly drifting through the wind, it is fast enough to act like a supersonic object in a fluid, generating a wake and forcing the plasma to flow around. Because of all this, this event has deep implications for how we view interstellar objects and how we view the heliospheric environment. If interstellar comets like 3I Atlas can exert this kind of influence, then the boundary between what we consider passive small bodies and actively interacting obstacles becomes blurred. Objects that pass through may not be inert. They may actively shape the medium they travel through. This has bearing on space weather and space environment modeling as well. If such bodies arrive, they might perturb plasma flows in unexpected ways, potentially even influencing planetary space weather if conditions align. While 3I Atlas is far from Earth and poses no immediate threat, the conceptual possibility raises interesting questions about the frequency and role of such interstellar visitors and their interactions. It also opens up the possibility of using comet-solar wind interactions as a diagnostic of the object's properties. By measuring how the solar wind bends, slows, or deflects around 3I Atlas, scientists can infer the object's charge state, magnetic properties, outgassing rate, dust flux, electrical conductivity, and perhaps even internal structure. Such an indirect probe gives us a unique tool to study an interstellar body that we cannot land on or sample directly. The distortion of the wind becomes a form of wind echo, telling us more than just the comet's composition, but how it interacts dynamically with its environment. On the broader scale of cosmic evolution, if many such objects cross our solar system, and models suggest interstellar objects are common, then the cumulative effect of many interstellar bodies interacting with the heliosphere might contribute to subtle long-term modifications of the solar wind environment, dust influx, and perhaps even magnetospheric conditions around the planets. Each visitor is a messenger from another system, and each interaction a micro-event of cosmic exchange. The bending of solar wind by 3Y Atlas might appear small on a universal scale, but conceptually it places the solar system as a dynamic region of contact rather than isolated space. The event also emphasizes the value of multi-instrument, multi-observatory campaigns. Capturing this interaction requires spacecraft capable of measuring plasma, magnetic fields, dust, and neutral gases, not just optical telescopes. The fact that astronomers have already used large observatories to identify unexpected tail geometry, sun-facing plumes, chemical anomalies, and now solar wind bending underscores how intertwined observational astronomy and space physics have become when confronted with such a unique object. It challenges us to think across domains. Compositional analysis, plasma physics, heliospheric modeling, and interstellar dynamics all come into play. From a teaching and public engagement standpoint, the story is compelling. It underscores how objects from far beyond our solar system are not mere curiosities, but active participants in our local space environment. It beckons a new narrative. The solar system is not closed, not entirely shielded, but is visited by external wanderers, that both tell us about deep space and engage in a cosmic dance with our sun's influence. That strangers from the galaxy can invade our heliosphere and bend its winds invites a sense of humility and wonder. It reminds us that the sun's domain, while vast, is permeable and interactive. In terms of future missions and research priorities, the behavior of 3I Atlas may prompt a rethink. Perhaps we need to deploy spacecraft capable of intercepting or closely monitoring future interstellar objects with plasma instruments, dust detectors, and magnetic field sensors to directly observe how they interact with the solar wind. If bending is confirmed and characterized, then future missions might aim to get upstream and downstream measurements of the wind in the object's vicinity. This is no longer just a curiosity. It becomes a science objective with broad relevance. How do interstellar objects couple with planetary systems and stellar winds? What can they tell us about the materials and conditions in other star systems? How do they modify their passage environment? There is also a philosophical layer to this event. For decades, comets have been treated almost as static relics, icy bodies that slowly sublimated and gradually faded away as they looped around the sun. 3I Atlas challenges that paradigm by behaving more like a traveling spacecraft of sorts, producing directed plumes, interacting electromagnetically with its surroundings, and bending a stellar wind. It invites a re-examination of small bodies in space. Perhaps many of them, especially interstellar ones, have active roles to play in plasma environments. It blurs the line between mere particle and active agent. The bending of the solar wind also raises the question of scale. How large or how conductive must an object be to influence a plasma flow on the scale of millions of kilometers? What threshold of outgassing, dust loading, or magnetic field strength is necessary? 3I Atlas might serve as the first observed case, but determining the scaling laws would transform our theoretical frameworks. If its interaction is strong, perhaps objects only slightly smaller or less active could still generate detectable signatures, which future missions could pick up ahead of time. As 3I Atlas moves on, receding into interstellar space after its brief sojourn through our solar system, its brief encounter will leave data imprints. Observatories and spacecraft will record the wake, the tail morphology, the disturbed wind flow, and the magnetic field topology. That wake becomes a laboratory for heliophysicists, a moving object, a solar wind environment, and an interplay more dramatic than any static planetary system boundary. The implications extend to how we model the heliosphere. The boundary of our sun's influence is not just shaped by the sun and the interstellar medium, but by visitors too. Each interstellar object that enters could be a minor sculptor of the heliosphere, introducing new interactions that modelers must incorporate. In summary, the case of 3I Atlas bending the solar wind is an event that forces us to widen our thinking. It challenges assumptions about comets, about solar wind interactions, and about how objects from beyond our system behave when they arrive. It opens doors to new science, plasma-object interaction, interstellar matter coupling, heliospheric boundary dynamics, compositional inferences via interaction signatures, and even space weather implications of passing interstellar bodies. The sun's wind, once thought to gently carry comets along, now appears to be responding, bending around, diverting, maybe even battling a traveling interstellar object. And in that daily dance of charged particles and cosmic dust, we find a story of universal travel, of foreign visitors, and of our home environment revealed in new light. The story continues with the astonishing encounter of 3I Atlas and the solar wind, deepening the mystery and expanding the frontier of what a small body from beyond can do when it slips into our solar neighborhood. Having already revealed signs of its interstellar origin, its high-speed journey and unusual emission patterns, we now consider the broader tapestry of implications the bending of the solar wind presents. Implications that ripple outward through space physics, planetary science, solar system architecture, and even our concept of how the sun's domain interacts with the galaxy. Because 3I Atlas appears to bend the wind, we must ask, what is the scale and geometry of the disturbance? In planetary science, a planet with a magnetosphere will generate a bow shock, magnetosheath, and wake downstream. Comets typically generate ion tails, but not disruptions of the solar wind at large. If 3I Atlas indeed produces a bending of solar wind flow, then it effectively generates a mini magnetosheath, a region of piled-up magnetic field and diverted plasma. That region could extend thousands or tens of thousands of kilometers depending on how active the object is, how fast it is moving, and how conductive or magnetized its surroundings are. To understand this, researchers must map the extent of the disturbance. What is the length of the diverted flow? How far does it stretch behind the comet? And how much of the solar wind momentum is diverted, slowed, or deflected? Answering that will yield a new measure of how hard the solar wind is and how soft an interstellar object can be before it becomes transparent to the wind. Another implication lies in dust and charged dust dynamics. Comets, especially active ones, eject dust grains alongside gas. These dust particles may carry charge, be embedded in plasma, and exert influence via electromagnetic forces. In the environment of 3I Atlas, if dust is being ejected sunward and anti-sunward in complex patterns, then the charge state of the dust, the size distribution of the dust, and the interaction of dust with solar radiation pressure and solar wind become crucial. In short, the comet is not only a source of neutral gas, but a source of charged dust, which may in turn influence the surrounding plasma flow. The dust might act like a fluid obstacle, a sponge of charged particles, or a cloud that the solar wind must flow around rather than through. With this in mind, the bending of the solar wind may in part be a manifestation of dust-laden plasma interactions, not just magnetic or gas interactions. From a comet formation and interstellar body perspective, the findings invite speculation on how objects born around other stars might differ from those we know around our Sun. If 3I Atlas is indeed capable of significant interaction with the solar wind, it suggests that such objects can maintain unusual surface structures, volatile inventories, or electrical properties. Perhaps its nucleus is rich in highly conductive metals. Perhaps its dust cloud is uniquely charged or magnetized, or it carries a crust significantly different from typical solar system comets. These possibilities enhance the notion that interstellar objects are not simply extrasolar comets, but may represent a broader class of bodies, indigenous to other planetary systems shaped by cosmic rays, collisions, and ejections that give them distinct electrical and physical traits. In other words, the cosmic heritage imprints a difference, and the way an interstellar object interacts with the solar wind may betray that heritage more strongly than the visible tail. Thinking of space weather and planetary protection, the bending of the solar wind by 3I Atlas raises hypothetical questions. If such an object passed closer to a planet or through a planetary magnetosphere, would the disturbance it causes in the solar wind be perceptible as a change in magnetospheric dynamics or induced current systems? Earth's magnetosphere experiences the solar wind continuously, and we have sensors to monitor fluctuations. If a high-speed interstellar body were to pass through the near-Earth environment and bend the wind, could that produce a localized perturbation to the near-Earth plasma environment? While 3I Atlas is distant and poses no direct threat, the concept opens a new class of transient space weather phenomena, passages of interstellar interlopers acting as small plasma obstacles. Because these would be rare, the risk is low, but the idea reframes the solar system's plasma environment as open to perturbation from external bodies. In terms of mission planning, the encounter experience emphasizes the importance of flexible spacecraft monitoring. Most missions study planets, moons, asteroids, or comets bound to the Sun. Monitoring of interstellar visitors has been opportunistic. To fully characterize the bending of the solar wind and the plasma physical environment around 3I Atlas, one would ideally have a spacecraft positioned upstream of the object, sampling the wind before encountering the disturbance, crossing the disturbed region, and sampling downstream wake. Since no dedicated mission was ready for this object, the data comes from remote observations. The episode drives home that future mission architecture may require readiness to redirect spacecraft or place small probes into flyby trajectories of interstellar objects as they enter the solar system. The concept of fast response missions gains urgency. When an interstellar visitor appears, the plasma physics community must have an instrument-capable observatory ready, including magnetometers, dust analyzers, plasma spectrometers, and charged particle detectors, to characterize the evolving interaction in situ. Additionally, the bending of solar wind prompts a reconsideration of energy transfer processes. As the solar wind flows past an obstacle, some of its kinetic energy is converted into heat, magnetic field compression, turbulence, and wave phenomena. If 3I Atlas diverts the wind, the local plasma may become turbulent, heated, or generate waves that propagate outward. That means energy is being extracted from the flow and turned into other forms. Heat, secondary particle acceleration, possibly dust charging, and electromagnetic radiation. The surrounding plasma environment could become seeded with instabilities, and the object's tail might act as a waveguide for these disturbances. By studying the deviations in the upstream and downstream wind, scientists may measure how much energy was transferred or absorbed by the object. That could yield a quantitative value of how strongly a small body can couple to a stellar wind. The connection also reaches into astrophysical context beyond our solar system. In many star systems, stellar winds interact with planetesimals, comets, asteroids, and escaped objects. If interstellar bodies like 3I Atlas can significantly influence a stellar wind, then we must revisit how common small-body wind interactions are in extrasolar systems. For example, in a young system with a strong stellar wind and numerous outbound planetesimals, the cumulative effect could shape how dust and gas are cleared, how the interstellar medium is enriched, and how the circumstellar environment evolves. The case of 3I Atlas becomes a micro-analog. What happens when a star's wind meets foreign bodies? What kinds of wakes, dust trails, magnetic perturbations, and waves are generated? These processes might affect disk clearing, planetesimal ejection, and the interstellar absorption of material. In that light, the bending of the solar wind around 3I Atlas is not only a solar system oddity but a sample event of astrophysical significance. Another dimension lies in the dust trail and eventual contribution of such bodies to the interstellar medium. As 3I Atlas moves out, it leaves behind dust, gas, and perhaps charged particles. That material will eventually merge into the interplanetary medium or heliospheric tail, and when it exits into interstellar space, it carries signatures of its passage and interaction. The bending of the solar wind could channel or sculpt that trail, perhaps even cause a localized density enhancement or magnetic signature. Future instrumentation in the heliosphere might detect such trails long after the object's passage. In essence, each interstellar visitor may leave a fingerprint in the solar wind and heliospheric medium. Over cosmic time, a succession of such visitors could cumulatively contribute to the structure of the heliosphere's boundary or the distribution of dust and plasma in our solar neighborhood. From a philosophical and outreach standpoint, the event reframes our sense of the solar system's vulnerability and openness. We often think of the sun's domain as a protective bubble, buffeting the interstellar medium and shaping the motion of external particles. But here we see a foreign body entering that bubble and altering it in a measurable way. It underscores that our heliosphere is not an isolated fortress, but a permeable region subject to intruders and interactions. That invites public fascination. A comet from another star enters, and the solar wind bends around it. It is at once sublime and humbling. The image of the sun's constant flow being shaped by a fleeting visitor from the galaxy gives dramatic flavor and underscores how connected our corner of space truly is. In the domain of theoretical physics, the scenario invites fresh modeling of plasma body interactions. The classic fluid mechanics approach might treat the solar wind as a magnetized fluid and the comet as a solid obstacle causing a bow shock. But the details here are more subtle. The comet is active, emitting gas and dust. It is moving at great velocity. It may possess induced or intrinsic magnetic fields, and the background plasma flow is non-uniform, full of turbulence, waves, and shocks already. The bending of the solar wind necessitates a more nuanced model, one that includes multi-fluid plasma electrons, ions, dust, charged dust coupling, magnetic field draping, and transient shock formation. If researchers can apply the case of 3I Atlas as an experimental point, it may improve our understanding of how mini magnetospheres form and evolve, how dust charging is handled in fast flows, and how plasma wakes evolve behind obstacles. These concepts have application from small comets to moons, from asteroids to space debris, and even to artificial satellites where plasma interactions matter. Looking beyond the bending of the solar wind suggests future observatories might look for similar signature trails to detect past passages of interstellar objects. The heliosphere might contain the ghosts of previous interlopers, undetected comets that passed and left imprints in dust, magnetic field anomalies, or plasma disturbances. By analyzing the solar wind and heliospheric current sheet for unusual kinks or stripes, scientists may reconstruct a record of past interstellar objects. The case of 3I Atlas thus offers a calibration: how big an object must be, how active, and how fast to leave a detectable signal. With that calibration, archival data might be rescanned to find past events where the wind was momentarily bent, perhaps unnoticed at first. There is also the educational benefit of such an event in teaching about cosmic scales and speeds. 3I Atlas travels at tens of kilometers per second, faster than many solar system objects. That speed makes the interaction highly dynamic. The relative velocity between comet and solar wind matters enormously. As a teaching example, we can contrast a typical comet bound to the sun, lazily orbiting, versus this visitor hurtling through at high velocity. The solar wind unable to simply deflect it slowly, but forced to react instantly and dynamically. The bending phenomenon brings to life how the solar wind is not an invisible static breeze, but a charged, magnetized, high-energy stream, subject to disruption by even small but fast-moving entities. Students can grasp that in terms of fluid dynamics and electromagnetism in space. Imagine a meteorite entering a river at high speed and causing eddies, wake swirls, and diverted flow backwards. Except here, the river is a stream of protons and electrons, and the meteorite is a comet from another star. As the event unfolds, there will be specific observational programs designed to measure the specific nature of the wind-comet interaction. That might include monitoring the magnetic field ahead and behind the comet's path, looking for draping of the interplanetary magnetic field, measuring particle flux changes when the solar wind meets the comet's outgassing plume, and modeling the dust cloud's charge and motion. Those observations may quantify how thick the plasma boundary is and how much the solar wind is slowed or deflected. By gathering that data, scientists may be able to derive numbers for the effective cross-section of the comet as a wind obstacle, the equivalent to an aerodynamic cross-section in classic fluid mechanics but applied to a plasma environment. That may lead to a new metric: plasma interaction strength of interstellar objects. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I Atlas bending the solar wind unexpectedly? We want to hear from you. Thank you for watching, and see you next time.